to share it with new people as well, and how it's matured and lessons learned. It's kind of the big thing. So thank you for that introduction, and I'll just kind of get right into it. One of the things when we're starting this, you're maybe thinking, how is this presentation going to be relevant to me? So I'm sitting here and I'm in manufacturing, or I'm in a different industry than oil and gas. And it's a good question. And I tried to build this presentation more to how it can be relevant to everybody's industry. Because what we do at KDC Reliability is we create programs that puts a measurement system in place and either mitigates or in some cases eliminate medium to high risk items in a very, very cost effective manner. So I'd imagine just about everybody that's sitting here now, and we can kind of talk about it towards the end, deals with, in some capacity, some level of reducing, mitigating, or eliminating risk in your field. So that's what we do. And there's an old saying, and I'll say it probably a couple of times: stagnant programs without measurable and continuous improvement policies often lead and produce quicksand results. And I totally believe that. And so when we're installing these measurement programs and these measurement systems, I think our responsibility is to try to remove as much bias as we possibly can. And it's something that we work on every single day, just to take a lot of that subjectivity out of our measurement systems. So without further ado, if you can listen to this maybe, and the systems that we install them to actually measure and continuously improve, not to make somebody wrong, but to improve systems, because the systems that we deal with kill people. So there's a high consequence of failure. So if you can listen to it, and if you get one thing out of it, that'll be successful on how I can go back and maybe contribute to what I'm doing in my job. So I'm not going to stay on this. I'm actually 26 years. This is my 26th year in this field, in 5 countries, highly certified. I'm not going to stay on that. I have been published in magazines, white papers throughout the country. So I just want to kind of throw it out there, because you might think, who is this guy to speak on this topic? So I've been around a little while. Jared knows this story. Kayla knows this story, but I want to share with everyone. In 2011, and this is kind of the why of why I designed what I designed and what I'm going to show you. In 2011, it was something that happened in a refinery in South Texas. And guy that I got very, very close to, we would meet at the coffee pot every day after our safety meeting. He loved baseball. I love baseball. And we'd meet up, and he had a 5-year-old son that was just getting into t-ball. And he wanted to become he was their coach. And we'd meet at the coffee pot, and he was so excited that day to share with me these practice plans that he had come up with for his t-ball team, 5-year-olds. And I said, man, you understand that, look, you're going to probably have your son and maybe one other person that's going to be really good. And you're going to have to stop people from picking flowers. So your practice plans, I said, man, tell me how that goes tomorrow. And we laughed, and he went in the plant and I went in the plant. And about an hour later, I heard a boom. It sounded like a shotgun, which is, I said, we in South Texas, maybe it's just part of the atmosphere. And when we were leaving that afternoon, we found out that my friend never made it to coach his t-ball team, and his son and his wife lost a husband that day. And the root cause of the accident ended up being a chemical injection point, which is a high consequence, high probability of failure item inside of a refinery. Lost containment and blew off like a bullet and took half of his face off. And so he's dead today. And right then and there, I said, you know what, we have to do something that's different. We have to challenge status quo just a little bit, and not to be rebellious, just to continuously improve what we do. And in our voices, our education makes a difference. And, sometimes we just need to speak up. And the world lost a good man that day. And it happens too many times over the course of a year, and we can do something about it. So without further ado, a lot of the things that I've done before, I've studied with Lloyd's, We looked at data sets of 100 of the worst losses throughout the entire world. You'll see I've studied some with the Chemical Safety Board and really started to understand the root causes of other accidents that Lloyd's didn't study. Right now, we're doing a pretty in-depth study on accidents that happen that are being investigated by the European Commission and getting down into the root causes of what those are. So if we can get down to the root cause, we can understand how to improve those. And so it wasn't to make anybody wrong or you're not doing the right thing. We just want to understand where the problems are actually happening. These 100 losses that you see on this pie chart that Lloyd's put out, just in business interruption alone was worth $250 million. That's not counting the refabs, the remanufacturing of the equipment. That was just the downtime, the fines, the lawsuits, loss of life. None of that was included in those figures. So you can see refinery is a big piece of what we do in this industry. I'd imagine in your industries, you have a pie that probably looks like this and different opportunities that you can really make a difference. Refinery just so happens to have a lot of damage modes, a lot of failure factors that's used throughout the processes that contribute to catastrophic failure. So as we go on, and some of the things that were really important to us, because we affect the mechanical integrity failure side of things, and we can start to control those. 43 of those 100 losses were due directly to mechanical integrity. Controllable, very, very controllable type situations like my friend and the bull plug situation that I mentioned earlier. And so out of those, this is what resonated with me the most, is out of those 43 failures that sit inside of mechanical integrity, 72% of those happened in a normal operation. Plant was flowing fine, not in an excursion, something out of its what we call integrity operating window. It wasn't in any of those. It's just a failure happened in normal operating times. In your facility, it might be failure happened in just the normal everyday opportunities that happen inside of your facility. Maybe something went bad and you can control those. Inspection program was a big one in this case that contributed to the mechanical integrity failure. I won't get into a lot of these other pieces, but there's what happened with this study, and the study that we use when we go into the European Commission inside of the Chemical Safety Board. Lloyd's is really starting to understand the problem, and I know people can do that in their fields. Just really, really wanting to understand the root cause and how to properly contribute to improving those efforts. We won't stay too long in there. Chemical Safety Board I started with Lloyd's. Lloyd's opened my eyes to the root cause of failures, and I said, okay, that's Lloyd's way of looking at things. Possibly other people look at it differently. So I went to the Chemical Safety Board, looked at failure investigations, really, really studied those, and it was really cool. Let me get this off of here. It was really cool, I thought, what the Chemical Safety Board said, and they published this, that in many refinery investigations, mechanical integrity programs repeatedly emphasize inspection strategies rather than the use of inherently safer design to control the damage mechanisms that ultimately cause the process. And what they're saying is we pick less expensive ways to build a facility, but we use inspection and understanding how damage manifests. We use inspection to properly predict the future. And we do this on purpose. And we do it in a cost-effective manner. If done correctly, your plant shouldn't be down. Uptime should be maximized. Nobody's getting hurt. Unfortunately, as our infrastructure starts to age, that's not the case at all. So the Chemical Safety Board, after being with them for a long time, probably over a year's time, really confirmed what I had learned with Lloyd's. And I said, okay. And then that's why I moved over to the European Commission to see what's happening around the world as well. And the pattern is the same. It's continuing to be the same pattern. And I'm going to tell you what those root causes are in a minute. So as a reliability engineer, we look for repeatability and reproducibility constantly. Like how well can I repeat my excellence? How well can Chad repeat his excellence every day, and what he's contributing to the overall focus of what we're trying to accomplish. Reproducibility comes in later on, and when us as a team can reproduce. So Jared Gaspar can reproduce my excellence, and then you have a whole team that starts to reproduce excellence on an everyday piece. That's hard. We're humans. We have bad days. You know, we're maybe not trained properly, or whatever the case may be. I wanted to bring up best practice codes because in our industry, these are the regulatory codes that contribute to how people do business. So people follow these codes, follow what's in the codes. They're still best practices though. And so if you pick these, you have to follow them, but there's so much leeway in there as far as the owner user having the ability to kind of maneuver around. And so I skimmed the codes that we use. And the three major ones are API 510, which are pressure vessels, piping systems, 653 are tank systems. API 580 moves into a risk base. And I look for any kind of term that said repeatability or kind of even looked like repeatability inside these codes. The pressure vessel code had one instance when it talked about repeatability, 2 instances in the piping system, and these were very, very small, just talking about an inspection wise. That we're, to look at some of the same spots to establish corrosion rates, and that's it. Even in the risk-based code, a risk-based code, which is all about confidence, it had some form of repeatability 5 times, and that's it. And this is a quantitative way. 580 is the whole picture, but there's 581 that looks in the quantitative way to measure damage mechanisms, and repeatability just didn't really show up many times. And so when we have codes dictating, and I'm not against the codes, I'm just for improvement in the codes. I'm certified to all these codes, and there's an improvement opportunity in these codes to say, hey, let's start to document and measure repeatability just a little bit better. So I wanted to show this, and these are the codes that are dictating. These are regulating our industry. So quite astounding, actually, when I scrubbed these codes and found not many instances of talk about repeatability. So after studying, and the European Commission is saying the same thing, after studying with Lloyd's and studying with the Chemical Safety Board and all these other teams, the lack of understanding damage mechanisms, how failure modes, I guess we can call it. So whether you're in whatever kind of industry, there's ways that things fail. And how do you inspect for those? How do you mitigate those? You first have to understand how they fail. And in our industry, in this industry at least, the lack of understanding how things failed, so the lack of understanding how to actually mitigate them, was the major contributor to most of the most catastrophic failures ever seen in this world. The lack of what I call a concurrent engineering process, where this guy here and this lady here knew what, or maybe that's a lady, they were actually communicating, and everybody in this circle actually were able to exchange information. They had knowledge exchange campaigns in place. And when something a damage mechanism was manifesting outside of its integrity operating window, that all 4 or the whole group knew what was going on. Communication is a big problem in our industry, and when something happens, it's never communicated. That was a root cause of some of these catastrophic failures, and it just the neglect of a repeatability, much less reproducibility program in place, is just front and center. This here is a contact tower, and you can see the contact tower here. It looks small on the actual, this is in Texas, by the way. This contact tower is a 100-foot vertical contact tower. This piece of equipment is 100 feet tall, and it's flying across the air like a missile. And this was due to a lack of understanding damage mechanisms, and that's not safe. So what we designed, to kind of move into what we designed at KDC Reliability and have been designing now for about 4 years through the proof of concept, probably 5 years, through the proof of concepts, through the implementation, to try to raise the level of effectiveness in what we do in this industry to try to eliminate contact towers flying through the air like missiles, or like my friend getting a bull plug taking half of his face off when he was just trying to go to work and provide for his family. That's just irresponsible. So what we built is the program is just, it's built for communication, for one. It's built on 4 cornerstones, and you can see the 4 cornerstones here: the scientific engineering, technical mechanics, auditing, and safety down in here. And the 4 cornerstones, what ends up happening, the technical mechanics piece compromises of the elements that address the precision and accuracy of the entire periodic chart, which I'll show you in a minute, and all the elements in the periodic chart. So you're looking, all of those elements contribute to the maximum effectiveness of the reliability moderneering program. The scientific engineering provides all the again, more precision and accuracy, again, to every single one of the other elements. The safety piece, we are perfecting algorithms that predict human deficiencies, and we're getting pretty good at those. So some of the AI and machine learning possibilities are coming in. So we're, humans will human, and I always say this: humans will be human, and we mess up. And so how to predict those, how to predict when a guy's or a lady's having a bad day. We've become pretty good at that here recently. We're getting better. That's a big piece. And then just, an audit system, because this whole piece is an audit system. And there's a lot of responsibility when it comes to auditing something. And, we're trying to provide a closed loop, auditable, measurable system that allows for reliability growth. And it really all starts with the quality piece. And you'll see elements that contribute to the quality, and elements that we need to measure for reliability as well. And then what we're trying to do is eliminate, and it's a strong word because it's very difficult, because there's so many factors that come into play, but due to mechanical integrity, which are factors that we can control, due to mechanical integrity, we're going to eliminate medium to high risk failures. And we'll know about them before they actually fail. And we're moving to do a pretty good job of that now. So here's the periodic chart. There's a whole fabric that's built into a software program for this, that has a whole audit system on the backside. And the system is built to programmatically find the actual element that affects the highest change that can be made at a certain period of time. So if CML optimization number 2 is the highest contributor to raising the level of effectiveness in your program, in your facility, in your site, in your objective, it's going to programmatically shoot that out. And then what happens is there's many other elements that are actually part of. So CML optimization can actually have an effect on 5 different elements to raise the level of effectiveness in 5 other elements, therefore raising your overall effectiveness. By concentrating on one element, your overall effectiveness can go up 10 to 15%. So what happens a lot of times, and just talking to a guy from Exxon here recently, and he said, the thing, whenever we pay attention to certain elements, like in your periodic chart, then other elements don't get the deserved attention, and then those start to fall out. And so we measure that too. And we want to make sure that, what we're working on and the progress we made, that it keeps that progress and we keep moving forward. So you can see element 5. And one thing I want to show you is that the periodic chart within the software program is weighted due to system risk. So everything that's on the top layer of the periodic chart has 100% weight. So any of these elements are critical to overall success of the reliability monitoring system. And as you move down, 80% system rank, 60% system rank, and then 20% system rank. And what's funny is field inspection is way down, and it's weighted at 20%. And people are like, well, man, field inspection is so important. why would it be at the bottom of your periodic chart? Everything on this periodic chart is important, every single bit of it. But for field inspection to be a contributor to overall improvement and for us to make proper predictions of future due to future equipment, for future equipment, excuse me, a lot of things have to happen at a high level before field inspection can even be a contributor to that. And that's what we've built here. So the whole measurement system comes out, and I'll show you in the lessons learned, and very hard-headed. And there's some lessons learned at the end that you really start to, I really need to, and our team really need to listen to our clients. So we kind of had this static fabric built software that has these elements, and there's gauges all throughout this thing, and how effective are you, and we built this fabric to just be static. And this is the way we see it, and this is the way everybody needs to see it, and they need to conform to us, and all these things, right? Well, quickly you find out that that's wrong. And so what we've allowed, the system weight, this top line needs to be there, and everybody agrees with us that we've talked to so far. What happens between element 6 and 23 sometimes can be scrambled around depending on what the client's trying to accomplish, their maturity and their mechanical integrity campaign and journey. So they're allowed to actually move these elements around, and then it recalculates how it affects the entire program. So that's something new we're working on right now. It's in development. It's something that I kind of saw coming, but I didn't think was going to be a thing, and I needed to probably listen to myself and other people, and I didn't, but I learned. I'm going to kind of get through this. I want to show you back in a proof of concept stage, which is a couple years ago to about a year ago. There were 3 refineries that we studied. The first one, and you can kind of see the table. So what's happening, this is just a raw data of the process effectiveness, and you'll see element number 1, system dynamics and layout. This refinery was 83% effective, and so on and so forth. And you can start to really see how this program laid out in here. And before, as I was dealing with this refinery, and there's a caveat to this, I want to make sure this refinery no longer exists. And it no longer exists not because they shut down, it's because they had to. And in this very unit that we studied, this hydrofluoric acid unit, just a brief understanding of hydrofluoric acid. When hydrofluoric acid fails, it makes a vapor cloud. And there were explosions everywhere, and it took over a little small city. So it's about a 10 to 15 mile vapor cloud that comes out. And this refinery no longer exists. But I did this study before it happened, probably about 6 months, I guess, before this thing happened. Long story short, I only had this table here, this 31% table. I didn't have this table here. And this is another lesson learned I just wanted to share with people, just because I was hard-headed again, right? So I went in there and we did a study, and it was 31% effective. And that's what I came out to. And the guy said, man, thank you so much for spending time with us. Like, we really enjoyed, what we learned from this study, and we'll get back in touch with you. Well, they didn't get back in touch with me. And then there was an explosion, and then the guy ended up speaking to me, and he said, hey, look, I just wanted to tell you what you designed was brilliant. But if you honestly thought I was going to bring 31% effective to my boss, you lost your mind. And he said, I don't know what you need to do, but you need to do something that can contribute to us actually installing this kind of program, because it's needed, but it can't make the client wrong. So, and so I thought about it, and what ended up happening, we built, because of the data that we had collected, we built a chart, or measurement system, that said, okay, how well are they those codes I showed you at the beginning of the presentation, how well are they following the minimal standards of the jurisdictional codes? How well are they doing that? And so we started to study that, and it's like, man, they're doing really, really good at following those codes, like really, really good. But there's opportunity, obviously, for these things to be just measured differently. Because we're not just talking about inspection now, we're talking about communication, quality, all the way to reliability, training, understanding, and everything that's involved in running a plant and keeping a plant actually up and running and not failing. So we found out quickly, 93%, they were effective. They were just about as excellent as you can be following jurisdictional codes and the minimum standards set in there. And so I called him back and we talked about it. And he said, if you had come with that, he said, we wouldn't have eliminated that failure. Those failure modes were too far gone. But this is something for the future that you might want to think about, to be a partner with the client and not making them wrong and you right. So I learned that. You have to humble a little bit. Refinery number 2, kind of the same. This one was only one unit was studied. It was an FCC unit that previously had 12 days of unplanned downtime in the previous 6 months. Business interruption alone was 18 million. It was a pressure vessel failure, and it was due to mechanical integrity. Very catchable, could have eliminated it, could have brought it down before the failure, but didn't. And you can see again, 89% effective following the jurisdictional codes and the minimum standards, 36% effective. And this is only one small unit. This is not the rest of the units in a very large plant, this one here. And once again, same thing. This was a crude unit studied, and this is all proof of concept because I'm trying to make myself wrong now. So I've gotten into this piece where, hey, people are doing the right thing. Like these all have to be one-offs. So I have to be wrong. And same thing. Crude unit, 26 days of unplanned downtime in the previous 12 months, $17 million of business interruption, and these were due to piping and exchanger failures. And all of these programs have been in place for many years of trying to predict failure. And obviously some things are going wrong. And so after this last proof of concept, we moved into actually implementing. And it's being implemented right now into a refinery as we speak now. And a new one's fixing to kick off here pretty soon. But the lessons I learned, and I wanted to share these because I'm sure anybody can chime in, and I'm sure, be open to client objectives. I was stubborn. I designed this thing and it was my baby and I wasn't changing it. And quickly the industry slapped me in the face and said, no, you're going to change. We like it, but you're going to change it. And I didn't change the integrity. The integrity and the foundation is still there. I'm not going to twist over and devalue the integrity that's built in here and what the system contributes. At the same time, it's what is the client trying to accomplish, and how well can we take what we built and put it into a system like this and actually measure it. And if you're thinking this is just oil and gas as well, we're actually going in underground infrastructure and building a system like this. There's one in manufacturing building a system like this. So there's opportunities that exist all over the field and all over the place. And we're looking at medical field right now, pretty hot and heavy to implement a system like this. Different elements, but the same kind of measurement tool. So there's opportunity for this to happen everywhere. We added element 18 here recently, and we're working with a company that uses machine learning and AI to predict failure mechanisms. And we tap into operational data from a non-human side. And we're just looking to make this whole system impervious to human corruption, because again, humans will be humans, and we just try to protect ourselves, but that doesn't lead to continuous improvement. And lastly, thing I learned is, because I'm impatient, and just to continue to fight the urge to mass implement this system and just start putting it at refineries and chemical plants and power plants and nuclear plants and this place and that place and medical field, and really understand. And we've had some early adopters that work well with trying to improve this process with their data. So we want to make sure we understand and we listen to what the data is saying, and we improve the algorithms that are built inside of here to actually eliminate what happened to my friend and having his head blown off. So we're continuing to fight the urge to mass implement, and that's hard for me. So we're going to continue to do it. I wanted to kind of show you. So again, like I mentioned, currently the system is being installed in two U.S. refineries. There's a baseline. It's Northern Refinery. Baseline was almost a year ago. They were at 42.6 effective. They were actually better than most. They were better than everybody in proof of concept as far as where they were effective. They were effective 92% in those regulatory codes. And right now, after 1 year, they've had a 10.5% increase in effectiveness according to these codes here, which we're figuring out what that is in value. Value as in money, uptime, business uptime, and how it affects the overall plant. We're doing that now. So it was kind of a cool way to look at it and actually, hey, these are some wins that we can celebrate, that we're actually moving forward. And these systems actually allowed us to kind of tighten up our algorithms too and say, hey, we can do a better job. And I think we can get to the effectiveness that they want a little bit quicker because of some things that we're learning. Kind of a current focus and ROI and kind of where we want to move to is we started talking to facility insurers, and insurance rates have gone through the roof in the last few years significantly. And risk-based programs that were actually installed in a lot of these facilities didn't produce what the insurers thought they were going to produce because they can be manipulated so bad. And so what they did is they backed out from any discounts that they were receiving in a lot of these, especially refineries. And so we're kind of coming in as the middleman from the owner user to the facility and kind of being that liaison between both of those, where the facility can actually understand their risk and how to mitigate it, and the owner user mitigate their risk, and the facility insurers start to gain confidence again that a third party group is actually measuring this system without bias. And COVID kind of slowed down those talks, but now those talks are really starting to fire up again. So this whole system is about building confidence and eliminating failure. It's what it comes down to, and how you measure that. There's a great responsibility in that measurement system. And so we're constantly improving that measurement system. And where it started 5 years ago to now it's light years away. So I just wanted to share some of the progress that we've made. And reliability growth is up to each and every one of us. We contribute. Whatever facility you work in, whatever office you work in, you contribute, or you have at least the opportunity to contribute to reliability growth in whatever field you're in. I know it, and it all starts with us. It's for us to see things, have a voice, get knowledge, have the courage to speak up, and stop some of these catastrophic failures that are happening in a lot of industries.